I'm Cecilia Testart, and in this presentation, I'll be showing you our work in finding and profiling BGP serial hijackers. This is our work done in collaboration with Philip Richter and David Clark at MIT, and Alistair King and Alberto Denotti from CADE at UC San Diego. And this was originally presented at the ACM IMC conference last year. So our motivation for this work is the fact that BGP hijacking is pervasive in the internet. As you can see here in these headlines, some of these very known hijacks are from a long time ago. So this one that I'm showing is from 2008. But the other ones are much more recent, from just last year or even earlier this year. So even though it's known for a long time, BGP hijacking is still a problem that is far from solved. And in trying to find evidence of this hijack, I realized that sometimes operators disclose these hijacks in mails sent to NANOG. And going through the mails in NANOG and noting the perpetrators of this hijack, we found that there are networks that repeatedly hijack over different periods of time. And we start calling this network serial hijackers. So these are networks that hijack a prefix at some point, and then a few times later, there's another evidence of some other prefix. And let me tell you the story of one of these quintessential hijacker that I call, which is BitCanal. So this network, there's evidence of its hijacks that comes to light for the first time in a blog post in September 2014. And it keeps being connected to the network. Then again, there's another blog post with some evidence of other hijacks that come to light in January 2015. And then 3 years later, there's a lengthy email going on in NANOG where the author is calling to the transit provider to disconnect this network because of the large evidence of repeated misbehavior of this network. And this network ends up being disconnected in July 2018. So it took 4 years for this network to be disconnected, for this serial hijacker to be disconnected. And I was inspired by this, and I'd like my research to help to improve that. So to do so, the research goals of this work was to find serial hijackers in the internet and identify their distinctive routing characteristic, then use them to build a machine learning model that would allow us to look at the behavior of more networks in the internet and flag the suspicious ones, evaluate the results of our classifier, and finally see what we can learn from the serial hijackers. So the first step in doing this is to find a ground truth for serial hijackers. So going through many emails for about 5 years on the NANOG mailing list, I ended up finding 3 networks that I call serial hijackers. These networks starting from the evidence of the emails, I'm able to find at least 10 prefixes that they have hijacked at different points in time. Most of these networks have been acting for over a year when looking at their BGP data. And also looking at their overall activity in BGP, I found that some of them have originated up to 30,000 different prefixes in the 5 years window of our experiment. And here on the right, you can see the map where the black dots represent the countries from these networks. And you can see that they're distributed more or less all over the world. There's not one country that has a larger concentration of them. There's some of them in Europe, in the US, in Asia, and in Africa. Then to keep on building this ground truth, I need the legitimate networks. And for that, I based my selection on the networks that agree to be part of these mutually agreed norms for routing security manners. So because these networks voluntarily agreed in increasing their or adopting certain routing behavior that would improve security, we interpret that as they wouldn't be persistently misbehaving, and that's why we include them as legitimate networks. At the point of the study, there were 191 networks that were part of this agreement, and we augmented them with 26 manually selected ASes just to add more diversity to the set of networks and autonomous systems that we were studying. So with that ground truth, then we need to come up with the BGP data for those networks. And for that, we use the publicly available collectors. So we use all Rybreeze and RouteViews collector. These are over 40 collectors, and there's over 1,400 networks that provide BGP information to these collectors. For the time window of our measurement, we process all the BGP updates that are sent by the different networks to these collectors to reconstruct the routing tables of these networks. From those routing tables, we extract the prefix and origin AS in the BGP path, and then we count how many peers have a given prefix and origin AS in the routing table, and that gives us the visibility of each prefix and AS pair. And we do this from January 2014 until the end of December 2018. So it's a 5-year window. So at the end, we end up with a database that has prefix, the origin AS, the visibility in terms of the number of prefixes that have that given prefix AS in the routing table, and a timestamp from when we computed this. And this is every 5 minutes. So with this very large data set of all these BGP information going on in BGP, a first step was to try to understand the behavior of networks in our data set. And for that, we used a graphical representation that allows us to better understand the behavior of network. So here, for example, is a graphical representation of an AS of British Telecom. So this is a network in the UK, and here you can see on the x-axis are the dates of our measurement, and on the y-axis, each line represents a different prefix that has been originated in BGP by this network. So the green lines that you see crossing from one side to the other of the graph are actually prefixes that this network has been originating all the time. And in every 5-minute snapshot, we're able to see that prefix being originated by this network. And of course, you can see that some of these prefixes are start to be advertised in the middle of the graph. Some of these prefixes stop being advertised. And this is usual behavior that we would expect in network operators. And also you can see that there's a column in red, and it is in red because those are prefixes that reach a very low level of visibility in our data set, less than 15%, and that's why we graph them in red. And also you can see that this happened for a very short period of time. So although most of these graphs show a very stable behavior, there can be routing events that look a little bit different. So overall, this is a very stable behavior. And in comparison, this is the same, using the same representation, this is what the serial hijackers looks in this representation. So here you can see there's a large difference, mainly the amount of white that is in this representation. And that means that most of the prefixes that are originated by these AS are originated by a very short periods of time in our data set. And also you can see a huge contrast in the number of different prefixes. So this network originates over about 1,500 different prefixes in this 5-year data set, whereas British Telecom only originates about 200. So the serial hijacker BGP activity looks very different from the legitimate one. And now we need to derive features that are going to allow us to capture this difference in behavior. And from this example, it might seem that it's very easy, but of course there's variability in the behavior of legitimate ASes and serial hijackers. So here you can see some other serial hijackers, how they look like in this graphical representation. And here you can see other benign networks and what they look like in this representation. So these different graphs were our inspiration to come up with hypotheses of how a serial hijacker how the behavior of a serial hijacker would look like in our data set compared to a benign network. And one thing is that serial hijackers would tend to have repeated absence from the global routing table, because they sometimes they're originated prefix, sometimes they're not there. Whereas most benign networks, once they start originating prefixes, they keep on originating prefixes for a very long time. Then serial hijackers, when looking at the specific prefixes, they tend to have shorter origination times. Whereas again, in legitimate networks, usually they're, once they start originating a prefix, is relatively stable. Then we looked at the conflicts that the prefixes originated by this network could have with other networks in the internet. And our hypothesis was that they would have more conflict with legitimate networks, although we acknowledge that there are legitimate reasons why this might happen. And then again, we believe that the serial hijackers would have much more volatility in the count of prefixes that are being originated over time compared to benign networks. And for example, here is a graph that looks at the number of prefixes being originated by a given network in 5 minutes bucket. And on the left side, you can see Comcast, and you can see that it's mostly stable, except for a huge peak that lasted about a day, and then it goes back to a relatively stable level. And we reached out to them, and it turns out that at that moment, they had an infrastructure problem, which made them deaggregate most of their prefixes, and that hugely increased the number of prefixes that they originated during that time. In contrast, for the serial hijacker, you can see that this number goes up and down, and many times this line goes down to 0, which means that at that point, they disappear from the global routing table. And another difference between serial hijackers and benign networks is the fact that the IP that they use have a broader geographical distribution. So IP blocks are distributed by the 5 RIRs, and most networks have their IP resources from one RIR or from a few of them, but most of the resources are concentrated in one of them, given the geographical zone where they're operating. However, given that serial hijackers do not go through the delegation process that other networks go, they can use just any IP prefixes, and their distribution tends to be more equal between the RIRs and not be so concentrated. So to measure this, we use the Gini index, which is heavily used in economics to measure the inequality of wealth distribution. And here we measure the inequality of distribution of IPs per RIR. So a Gini of 0.8 means that all IP resources from a network are concentrated in one RIR. And in this graph, we can see that serial hijackers, the orange line, tend to have lower Ginis, which means that their distribution is more uniform between all 5 RIRs. So in our data, we found confirmation of this different behavior in this 5-point between serial hijackers and benign networks. And then we derived 52 different features that capture the different behaviors and the different flavors of this difference between serial hijackers and legitimate ASes. And then using that, we build a machine learning system to then run it with other networks. But there are challenges in applying machine learning to find more potential serial hijackers. The first challenge that we get is that our data is actually really heavy-tailed and skewed. And by that, what I mean is that in most of our dimensions, when looking at ASes, these networks, most of them concentrated in just one part of our dimension, but then there's the long tail that really extend the size of our variables. And then we have variables that are very different in size. So for example, one variable could be the number of prefixes that they originate in a certain period of time, and it could go to a few thousand. But we also have the Gini index, which just varies between 0 and 0.8. And these differences make it very difficult to normalize our data. Then again, we have a very small ground truth, because building the ground truth, at the end we end up just with 240 networks when there's over 70,000 networks in the internet, and of those networks, about 20,000 of them originate more than 10 prefixes. And lastly, we have a huge class imbalance, because we were able to find only 23 different serial hijackers, and we have over 200 legitimate networks. And we need to carefully train our classifier because of this class imbalance. So our approach to solve this is to use a tree-based classifier that is able to handle all these variables with very different dimensions. And we also use a voting ensemble of extremely randomized forests, because that allows us to train every different forest with a different base, a different base that comes from different sampling techniques. And that way, because each sampling techniques create the synthetic data points a little bit different, we're able to gather, to have a better trained classifier using this technique. And finally, for the 52 features that we built, we wondered if we could have select a few of them that are more relevant than others, but it turns out that looking at the accuracy of our model, every time we took one of the features out, it was less accurate. So we ended up having all 52 features because they all had a positive median drop columns importance. So at the end, using this approach, our classifier ends up having almost 80% precision and 100% recall. And what this means is that our classifier is able to select all the serial hijackers from our ground truth, but it always includes a few legitimate networks in that set. So knowing this limitation, we went and run this classifier in all the data from the networks that we got from the BGP collectors. So with the goal of finding networks with similar behavior to the serial hijackers, we started with these 75,000 networks that we find in our data set. Of these, only about a little bit less than 20,000 originate at least 10 prefixes in the 5 years of our data set, and we only run in the data from these networks. Given that if we're looking at serial hijacker, we'd expect them to have originated at least 10 prefixes in 5 years. Our classifier flags a little bit over 900 networks from this set. And this means that it's a little bit less of 5% of all the ASes seem to originate over 10 prefixes in those 5 years of time. And it's about 1.2% of all the ASes that we see in this 5 years data set. So with this result, we wanted to learn who were these networks. And the first approach was to look at their behavior in the same graphical representation that I showed you before. And these are the representation from networks that were flagged by our classifier. And we can see that they're very similar to the ones that we saw earlier. And then studying a little bit more, what are these networks? Well, we started first by looking if we could find any indication of malicious behavior in these networks. And the first place that we went to look at this were block lists. So we look at the block list from Spamhaus that tags ASes because of repeated criminal behavior. And we found that 84 of the networks flagged by our classifier are in the Spamhaus ASN drop list. This means that networks flagged by our classifier are 10 times more likely to be in this block list than the networks that were not flagged by our classifier. Then we looked if any of these ASes had originated prefixes at the same time that they had been blacklisted in spam blacklist. And it turns out that about a third of them have originated prefixes that end up being blacklisted at the same time. Then we looked for indications of misconfiguration. And in that we find that a little bit over 100 of the networks, now the ASes that we find are actually private ASes that should not be using BGP. And because there are misconfigurations and they happen all around the network and they're quickly corrected, they appear to have, when looking at just one network, very volatile behavior. And this is what gets caught by a classifier. And also we find that all the single digit ASes are caught by a classifier, and these come from these fat fingers errors when configuring sometimes the border routers. These numbers are added at the end for doing some prepending, but because of mistakes, they appear to be the origin in BGP, and it happens again all around the network. They're quickly corrected, and it looks like these networks have a very volatile behavior and connect to multiple points of the network, which is the behavior flagged by a classifier. And finally, we look at another category of false positive, which is networks that offers DDoS protection on BGP. To do so, these networks actually originate a prefix or a sub-prefix from the client where they're under attack, And this is a benign sort of hijacking. And again, this is exactly the behavior that we want our classifier to flag. And this is why we flag these networks. So after looking at all these categories, we're left with 441 networks, which we cannot immediately find in these categories. But in these over 400 networks, there's still some pretty interesting networks. So this is a network for which we couldn't really find any evidence, but looking at its behavior, it turns out that over half of the prefixes that it originates last for less than 12 hours. And over 80% of the prefixes are also being originated by other networks at the same time. And honestly, I think this is really interesting, and part of our future research is to try to understand any legitimate reasons why a network would behave this way. So just to conclude, 43% of the networks that are flagged by a classifier, we can find them in one of these known categories, but there's still these very interesting 47% left of networks. So we know that our classifier is not a bulletproof identifier of malicious ASes. Again, we are just looking for ASes that exhibit similar behavior to serial hijacker, not necessarily malicious behavior. And we also know that this doesn't capture all kinds of behavior. We're really looking at this repetitive sort of behavior. And also we're heavily focused on prefix origination. So this is just prefix hijack and would not include something like path hijack. So this work, for the first time, we bring to light these networks that we call serial hijackers and study their behavior in BGP. And with the different features that we derive to understand how benign behavior differs from the serial hijackers, they indeed end up giving us a state of affairs of BGP-wide behavior of networks. And the outcome of a classifier can indeed be used in network reputation scoring system as an additional input. And finally, our classifier really narrows our focus on these more interesting networks, which we would like to understand their behavior in the future. And with that, I'd love to get your feedback on how to continue this line of research so that this information could at some point be integrated in operational practice to make routing more secure. Thank you.
Yeah, thank you, Cecilia, and welcome. So we have you live here. Let's go and check if our audience has had any questions for you.
Okay.
So I'm just trying to scroll through and see. Okay, so it doesn't look like, other than the fact that people, concur with the fact that fast fingering has led to a lot of problems, I don't see a lot of questions. But let me ask you something. I found it very interesting, not coming from a security domain, but in terms of the data that you collected, what were the challenges that you faced in collection? Because you have to make sure you have good data so that your model and your machine learning can give you more legitimate and real world results.
So I think what is challenging is that these collectors captures the BGP data as it goes in the protocol, and as happens with the false positive, there's a lot of mistakes that can go in this protocol. So, for example, gathering this data, I could sometimes have a prefix coming from an origin that only one collector could see, but how could I be sure? Maybe it's some stall router that is sending that information, or something happened in the collector, so I need to discard it. So a lot of it at the beginning was trying to understand the data that I was dealing with, and how could I be certain after studying the data that certain part of it, everybody was seeing it. And that's when we started looking at visibility. And for example, all the things that were really not visible for like 1 or 2 points by the network, we discarded them because those could be just very local misconfigurations.
Okay, and I believe I see a question on the chat. So it seems hijackers also need a real link to get into the internet to be able to create disruption. So have you, in your research, have you investigated patterns, who these serial BGP hijackers pair with? Do you have any data or any insights into that?
Yeah, I think that's a really interesting question, and it's something that I'm working on as a future research. And for example, starting with this list of hijackers, something that I'm kind of investigating now, I realized that sometimes some of them, since they're originating, they have the same next hop, and somehow it seems that some of them have this structure where you have maybe this next hop that is not the one doing the hijack, like the origin hijack, but is the one that has the link to the rest of the network, that is providing for them a way to get into the network. So that's one thing. So there's definitely some structure on how they get connected to the network that is really interesting to investigate. And the other thing is, for example, in the case of BitCanal, the hijacker that was disconnected after this lengthy emission to Nanog, they reconnect to another point of the network. So they were disconnected by some transit provider, and then they found out a smaller one that could give them connection, and they got connected again. So I think this is kind of catching, and it'd be interesting that like a large part of the network actually blocks them, because otherwise they can always find point of connections.
Okay. So now we have some other interesting questions popping up. In terms of the speed of your machine learning processing, are you able to process a real-time stream of BGP updates?
I haven't checked the real time. I think we would have a lag for maybe half a day or something like that, as it is for the moment. So because this was a historical analysis, processing that data took a very long time because it was like 5 years of data. Once we have that computed, then adding a day of data is much faster. And this is based on BGP stream from CADA. And that system has about, I think, 30 minutes lag to 2 hours lag between real time and processing some of the announcement. And that would be like the faster that we could go. But this is not yet a plugin that is ready to pop in there.
And as far as the time horizon goes, how long it would take for you as you're doing your processing and trying to figure out how long would it take for you to classify, for your classifier to go ahead and flag a hijacker?
So once
you
I
are
have
processing a live stream.
Oh, if I'm seeing a live stream, well, it depends on the amount of historical data that I have. So some sensibilities that we've seen is that with less than 3 months of historical data from a network, it's much harder to figure out, is it doing a lot of hijacks or not.
Okay, all right. And in terms of, there's another question that is posed on the chat, is that have you guys been using geolocation as an input as well?
We haven't been using geolocation as an input. What we've been using that it's not as close is the RIR that is delegating the IP prefixes that are being used by the different networks. And we're checking the concentration of the resources that the networks use in the different RIRs.
Okay, all right. I think we have time for about as many questions, but if there are any more that come through, I'll make sure pass them on to you, so that we can get them addressed. But thank you so much. This was a very refreshing and insightful talk. And for a novice like me who shies away from security, I definitely learned a thing or two. Thank you so much.
Well, thank you for having me. Bye.